Hello students, I am your mentor Dr. Shri Wandel. Hope you are studying well at home. After today's lecture, you will be able to explain electric field lines and electric flux. Let us first consider a small positive charge placed in an electric field. Now this positive charge experiences a force in a particular direction. If this charge is set free, it will move in that direction. Now if the direction of force changes continuously, the direction of motion of this charge will also change continuously, and it will move along a curved path. Like this. This imaginary curved path is known as electric line of force or electric field line. Thus, the electric field line or electric line of force may be defined as that imaginary smooth path drawn in an electric field along which a free, isolated, small positive charge moves. The tangent drawn at any point on the electric line of force gives the direction of electric field at that point. Therefore, if we consider this point in the electric field, let it be A. If I want to find out the direction of electric field at that point, I need to draw a tangent at this point. Then this tangent will represent the direction of electric field at A. Now we will consider the electric field lines produced by an isolated charge, a system of charges, or a continuous charge distribution. Let us first consider an isolated positive charge. In this case, the electric field line look like this. the direction of the electric field is the radiating outward direction in this case. Then I consider an isolated negative charge. In this case, the lines of force will be in the radially inward direction. Okay. We may also consider an electric dipole. So you have a positive charge, you have an equal amount of negative charge separated by a short distance. As we know that electric lines of force are outward from positive charge and inward in case of a negative charge. So you can see that lines of force start from positive charge and end on negative charge. So this is the case with an electric dipole. As you can see that the concentration of electric lines of force is the greatest between the positive and the negative charge. So electric field is expected to be the strongest between these two charges. We may also consider two equal positive charges are separated by a very short distance. So you can see that you have two positive charges separated by a very short distance. Now, the electric lines of force in this case will look like this. from positive charge, electric lines of force are in the outward direction. So you can see that all lines of force are directed outward. But we consider a point in exactly midway between these two charges. At this point A, the electric field produced by this positive charge will be exactly equal and opposite to the electric field produced by this positive charge. As a result, the net electric field at point A will be 0. This A is known as neutral point. And no electric line of force will pass through this point N. So this is the case with two equal positive charges. Is that okay? We may also consider a long line of positive charges, or you may also consider an infinitely extended plane conductor. In both cases, the lines of force will look like this. The electric field produced in this case is uniform. This uniform electric field is represented by a set of parallel and equispaced lines. A uniform electric field means the magnitude of electric field is constant everywhere and they are directed in the same direction. Okay? So this is the case with an infinitely extended plane conductor or a long chain of positive charges. So this is practically an example of continuous charge distribution. Finally, we will also consider the electric field between two plane conductors. They are oppositely charged and they are having finite attraction dimension. So we may consider two parallel plates. They are oppositely charged. They are having finite dimension and ion interested in the electric lines of force between these two oppositely charged plane conductors. Okay? In this case, electric field line will be uniform in the central region. But if we move towards the edges, electric lines of force fringe. That means we get non-uniform electric field. So what you see that here electric field is uniform and here electric field is non-uniform. Okay. So this is the case with two oppositely charged parallel plates. Okay. The non-uniformity in the electric field at the edges can easily be explained. Let us consider one unit was pictured at this position, one unit was pictured at this position, and another unit was pictured over here. You can see that the force experienced by this unit positive charge will be 0 due to these two charges. Why? Because this unit positive charge exerts a force of repulsion onto this positive charge. Similarly, this unit positive charge also exerts equal amount of force of repulsion, but now it is in the opposite direction. So they cancel each other. As a result, we may consider that the electric field line is horizontal at this position. But if we consider a unit was pictured over here, another unit was pictured over here, you can now see that this unit positive charge exerts force of repulsion onto this charge, but there is no other unit charge below this which will apply force of repulsion in the upward direction. As a result, this line of force bends. Okay, and this is how we can explain very easily and lucidly why the electric lines of force bend near the edges. Is that clear? So again we have considered another kind of continuous charge distribution. Okay. Now we consider properties of electric field line. Okay. So number one is these lines of force are continuous, smooth, imaginary curves without any break. So they are continuous, smooth, imaginary curves without any break. they start on positive charges and end on negative charges. They do not form any closed loop. So we have considered 6 cases. We have seen that there was no such closed loop. Okay? Is that clear? If we consider any isolated charge, then they start or end on infinity. So for any isolated charge, they start or end at infinity. Okay. Number 3, the candidate drawn at any point on the electric line of force represents the direction of the electric field at that point. Number 4, no two lines of force intersect each other. This can be very easily explained. I consider 2 electric lines of force. I have these 2. I also consider that these 2 intersect each other at point P. If it is possible, I can draw 2 tangents at point P on these 2 dots. It means that the electric field at point P can have 2 directions, which is not possible. An electric field cannot have 2 directions at any point. So it means that no 2 lines of force can intersect each other. Okay? Now we are considering quite fine. The relative closeness of the lines of force is a measure of the strength of electric field. For example, if we consider electric lines of force are closely spaced, we already considered the case of electric dipole, and we mentioned that between the two charges we have various concentration of electric lines of force. So electric field is strong between 2 point charges. So when you have closely spaced electric lines of force, we have strong electric field. If they are far apart, it means that electric field is weak. If we have parallel and equally spaced electric lines of force, it means that it is a uniform electric field. Is that okay? Number 6. Okay, so the lines of force have a tendency to contact in length like a stretched elastic string. This actually explains the force of attraction between two opposite charges, and that's why they tend to contract. Okay, they have a tendency to expand in a direction perpendicular to their length. This actually explains the force of repulsion between two like charges. Okay, and that's why they actually tend to move away from each other. Number 8 is the lines of force are always perpendicular to the surface of a conductor on which charges are in equilibrium. This concept can be explained very easily. We consider a plane surface of a conductor, and we also consider that electric field is not perpendicular to the surface of the plane, rather it is making an angle theta with the surface of the conductor. In such a situation, there will be a component of electric field along the surface of the conductor. So this component of electric field would set up a current on the surface of the conductor, but no current flows in equilibrium condition. So we can conclude that the electric field is always perpendicular to the surface of a conductor. Okay. Finally, point number 9. The electric lines of force do not pass through a conductor, as the electric field is zero inside a conductor. So, we have discussed various properties of electric field lines. Okay. Now we will explain electric flux. For that, we need the concept of area vector. So first, we start with area vector. An area element may be treated as a vector. We consider a small surface area. The amount of this area is delta F. I consider a direction along the outward normal to this area. Then the area vector is represented as delta S arrow, which is equal to magnitude of this area vector, which is equal to the amount of the area multiplied with unit vector n cap, where n cap is a unit vector along the outward normal to the area. So if I consider this vector to be delta x, then this length actually represents the magnitude of this vector, and n cap is the direction, which is actually a unit vector along the outward normal to this surface. Okay. So in this way, we can represent any area by its vector. Now we will discuss electric flux. Electric flux is the property of the electric field. By definition, electric flux through a given area held inside an electric field is the measure of number of lines of force passing normally through that area. Okay, so we can see that the electric flux through a given area held inside an electric field is the measure of the number of lines is the measure of the total number of lines now we try to explain the concept of electric flux. So we consider an area element delta and we also consider electric lines of force like this. So you can see I have considered electric lines of force to be perpendicular to the plane of the surface element delta. In this case, the electric flux can be written as delta phi E is equal to E into delta. We are considering another situation. Here also I am considering an area element delta S, and in this case you can see this is the direction of area vector. Area vector is always directed along the outward normal to the plane of the surface. Now we consider that electric lines of force are making an angle theta with this outward normal. That means with the direction of the area element. So you have electric lines of force like this. In this case, I have to calculate electric flux in a different way. Now you take the definition. Here I mentioned that the total number of lines of force passing normally through that area. So what I need to do, I need to consider the component of electric field in the direction of the area vector. That means in the direction perpendicular to the plane of the given surface area. So if I consider this, I get this component to be equal to E cos theta. In that case, electric flux is defined as delta phi E is equal to E cos theta into delta S. Because now you can see E cos theta is the component of electric field which is normal to the given surface area. Okay. I can also consider the third situation. So I consider this to be the surface element. And here you can see that outward normal is along this. So this represents the direction of area reflection. Whereas electric field is acting in the horizontal direction. So let it be like this. This is the situation. So in this case, I can take projected surface area in such a fashion that electric field lines become perpendicular to the projected surface area. Okay? So for that, what I am doing, I am considering this projection. Okay. So if this angle is theta, this angle is also theta. In that case, this projected surface area becomes delta is cos theta. So in this case, electric field, or electric flux, I should say, electric flux can be written as delta phi E is equal to E into delta S cos theta. So from this discussion, it is clear that I may write electric flux delta phi E as E dot delta S. So you will get E delta cos theta over here, E delta S into cos theta over here. But here you can see that theta is equal to 0. Because if we consider delta S vector, then the angle between electric field and delta S vector is 0. In that case, cos 0 is equal to 1, and that is why you are getting delta phi is equal to E into delta S. So this is the general expression for electric flux through any given area. Okay? If electric field is non-uniform over a surface area A, we are considering E to be non-uniform. In that case, we divide this surface area into small surface elements, into small area elements, like this. Let us now represent this small area element as delta S1 and the electric field through this surface area, through this area element is E1. So for this small element, I should be writing it as E1 dot delta S1. If we consider another surface element or any element will be represented by delta H2. And if the electric field acting in this element to be equal to E2, then I should have E2 dot delta H2. So you have to go on adding all such terms. So you have n such surface elements. So last term will be En delta Sn. En dot delta Sn. So that actually gives you total flux funding. Okay. We can also represent this using a compact notation. So it can be represented as the I summation ER dot delta XI, where summation takes place over I, where I can vary from 1 to n. If this delta is to be tending to 0 and if n tending to infinity, in that case this summation is replaced by integration. In that case I will be writing phi E is equal to surface integration E dot dx. If we consider some closed surface, if we consider the surface of a ball, then this is a closed surface. In that case, for closed surface, phi is written as closed surface integration, represented like this, dot ds. Next we consider unit of electric flux. So you can see that delta phi E is equal to E into delta S, if I make it cosθ. So we already know that unit of this electric field is Newton per coulomb and unit of delta S is meter square. So we can say its unit is Newton meter square per coulomb. Earlier I mentioned that E can also be represented in terms of volts per meter. We will discuss it when we will be studying electric potential. So if I consider electric field to be represented in terms of volts per meter, delta phi E becomes volts per meter into meter square. So we get volts into meters. Okay. Similarly, we may consider its dimension. Now, if we consider dimension of flux, that is electric field multiplied by surface area. Electric field means Newton per coulomb. Newton means kg meter per second square. That is N is e to the power minus 2. By coulomb, coulomb means ampere second. So ampere into time. And you have meter square. So that is actually A square. So if you simplify this, you have A cube e to the power minus 3 e to the power minus 1. So this is the dimension of electric flux. Now of course, you already have seen that delta phi is equal to E dot delta S. So So that is nothing but dot product of two vector quantities. So this is a scalar quantity. So this is a scalar quantity. Okay. We now consider some special cases. We already considered delta phi E is equal to E dot delta S, that is E into delta S into cos theta. When theta is equal to 0 degree, that means direction of area vector and direction of electric field are parallel to each other. Or in other words, electric field is perpendicular to the plane of the area element. In that case, I have already considered this case. It is equal to E into delta S into cos 0 degree. Cos 0 is equal to 1. So this is E into delta S. If we consider theta is equal to 90 degree, that means now the angle between the direction of area vector and the electric field to be perpendicular to each other. Or in other words, the direction of electric field is parallel to the plane of the electric field. In that case, you can understand no electric line of force can pass through this area element. That is also evident from this. E into delta S into cos 90 degree, cos 90 is 0, so this is 0. If theta is equal to 180 degree, that means now the outward normal to the surface and the direction of electric field are making an angle of 180 degree. In that case, delta phi E is equal to E into delta S into cos 180 degree. Cos 180 degree is equal to minus 1. So I have minus E into delta S. Finally, the electric field strength at any point is proportional to the electric flux density. That means the electric field strength at any point is proportional to the number of electric lines of force passing through unit area. This unit area will be normal to the direction of the electric field. So I believe that you have understood the concept of electric field line and